Good day and welcome back to part 2 of our discussion on optimization problems. So just a quick reminder, optimization problems are very similar to related rates problems we encountered earlier this semester in the sense that they're going to come in the form of some type of word problem that we have to read through, decipher, draw a picture, introduce some notation, and very importantly, set up a function of one variable that we will maximize or minimize on a given interval, and then we solve that calculus problem. And we'll walk through an example in a moment. In our previous example, the calculus problem that we set up was one of these extreme value theorem problems of maximizing or minimizing a continuous function on a closed interval. And it turns out that we could maybe cut a little bit of our work out by using something called the first derivative test for absolute maximums. And what it's telling us is the following. I'm going to draw a number line to go with this. We have a function that we are hoping to maximize or minimize on a closed interval from a to b. And what we find is that c is some critical point between a and b. And what the first derivative test for absolute maximums and minimums tell us, and I will always abbreviate it as FDTAMM, that's just much simpler for us to write, is that if f prime is greater than 0 on a to c, so remember what that tells us. Greater than 0 would mean that we have a function which is increasing from a to c, and then f prime is negative afterwards, so decreasing. So if you have a function which starts off at a and it increases up to c and then decreases after, the only possibility is that c is not only a local maximum on that interval from a to b, it is the absolute biggest the function can possibly be on that interval. So then we could say that f of c is the absolute maximum value of f on this interval from a to b. And in the past, the first derivative test would have only told us a local maximum, but because of this scenario of having a single critical point on a closed interval, we can guarantee that it is in fact an absolute maximum. But you can only make this conclusion if you properly reference this new test, the first derivative test for absolute maximums. And note the analogous result holds if you're decreasing to the left of c and increasing to the right of c, then there's no other possibility except that f of c would be the absolute minimum value of the function on the interval. So let's go ahead and dive into another example and see how this can naturally arise. So we have the following scenario. An open top box has a square base and a surface area of 108 square inches. What dimensions produce a maximum volume? So we want to maximize the volume of some open top box that has a prescribed surface area. So let's go ahead and draw a picture. So we have some type of box, but it doesn't have a top on it. So roughly speaking, we have something that looks like this. And what we are told is that it has a square base. So let's assume that the length and width of that bottom base is just x. And then it's going to have some height, let's call it h, associated with it. And the quantity that we want to maximize is the volume. What dimensions produce a maximum volume? So the volume of this box is length times width times height. And this is a very familiar scenario that we will find ourselves in. This quantity that we want to maximize or minimize involves two variables. In order for us to have a calculus 1 problem to solve, we need to write this in terms of a function of a single variable. So somehow there's going to be some more kind of constraining information given in the problem that will allow us to rewrite one variable in terms of the other. And in this case, what we are told is that the surface area is 108 square inches. So what we are guaranteed in this problem is that 108 is the surface area. And if we want to envision or come up with a formula for the surface area, remember it's an open top box, and you could simply imagine almost kind of unfolding this. So what we are left with would be 5 rectangles whose areas we need to add up. You have that rectangle, or in this case the square, making the base, and then you have 4 more rectangles making up each side individually. So we're taking the area of the base plus the 4 sides area added together. And this is a very common part of the problem. We want to somehow rewrite the volume so that it only involves one of these variables, and we see that we can easily isolate the h in our equation to the right. So if you were to isolate h, we would need to subtract x squared from both sides and divide by 4x. And we can go ahead and substitute this quantity in for h. And if we do that, we would have the volume now as a function of x is going to be x squared multiplied by 108 minus x squared, all divided by 4x. And if we simplify this, which we certainly can, we have what, an x and an x that cancel. And then we will simultaneously let this x distribute through the top and divide each of those terms by 4. And when we do that, the first term will involve an x, and 108 divided by 4 is 27. And then we'll be subtracting away a 1/4 x cubed. And this is the equation that we want to maximize, and we want to maximize it on what interval? So I want you to pause the video for a moment and think of the given information. How small or how big can x be? And note, because x represents the length of a side of this box, it has to be at least 0. And note, 0 is kind of a contrived case, but it is a possibility. And also, the equally contrived possibility would be if h was 0, which would force x to be the square root of 108. And that's really just giving us some interval to work with. And every time we set up an optimization problem, you need to give me the function of interest, what you're going to do to it, on what interval. So this function will be maximized on a given interval. Now we solve this associated calculus problem. So we need to differentiate. Term by term, we would have what? 27 minus 3/4 x squared. And then we find any critical points. That is to say, we set this equal to 0, and we solve for x. So we would have 27 is equal to 3/4 x squared. So if we multiply both sides by 4/3, note 27 over 3 is 9, times 4 is 36, so 36 is x squared, and we end up with x being plus or minus 6. And recall, we are specifically interested in this interval from 0 to the square root of 108. So we can make an associated number line. We're thinking about v prime from 0 to the square root of 108, so some number a little bit bigger than 10. And in that interval, we have one of our critical points, 6. And this is precisely the scenario that the first derivative test for absolute maximums and minimums is made for. If we can figure out the sign of v prime in each of these intervals, we can apply it. And if you were to substitute into our equation v prime, your favorite number between 0 and 6, maybe 1 is a nice number, 27 minus 3/4 is most definitely positive. And if you were to substitute in a number between 6 and the square root of 108, so maybe say 10 would be a perfectly good number, 27 minus 3/4 of 100 is most definitely negative. So this critical point that we have at 6, if we think graphically what's going on, your function increases up to that critical point, then decreases after. So by the first derivative test for absolute max and mins, and it is very important that you include that information. Without this new test, we don't get that desired conclusion. But by the first derivative test for absolute maximums and minimums, x equals 6 is an absolute maximum. What we now need to do is make sure that we answer the question that was asked. We are asked specifically, what are the dimensions that will produce a maximum volume? So we know the base dimensions will be 6 by 6. What we need to know is the associated height. So the dimensions now, just to put this into a sentence, so the dimensions that produce a box of maximum volume are 6 by 6 by something, where that something is determined as follows. And just doing a small computation to the side, we can note if x is 6, h is 108 minus 6 squared, all divided by 24, which simplifies down to be 3, which gives us the height of that desired box. So lastly, let's just go ahead and throw that in. The dimensions of the box that produce the maximum volume will be 6 by 6 by 3, and because we are given units, I will throw the units of inches after that last number. And just to reiterate, as we did after our last example, the key ingredients that you need. A picture where you've somehow labeled those quantities that are going to change or vary. Coming up with an equation of a single variable, telling me if it's going to be maximized or minimized, and on what interval. So you absolutely need to include this statement. Then you solve that calculus problem and give a concluding statement. If you've used the first derivative test for absolute maximums and minimums, which we have, you certainly need to include that information. We will continue on with more examples in our next video, but once again, this would be a great opportunity to go through and practice some suggested problems. So stay tuned and take care.